I guess in some sense we could say that one of our goals of introducing energy is to be able to use this concept of the conservation of energy. It's sort of the pinnacle of success when we're dealing with energy. Where do we get that conservation of energy concept? Well, so far what we've done up until now is we've found that when we do work on a system, it results in a change in kinetic energy. As we introduced the idea of potential energy, we were also able to say that when that work is being done, there's a corresponding decrease in potential energy. We're using U for potential energy. If we equate the work terms, because they are the same, we can then make a relationship that is exclusively dealing with the energy terms. That is, we can say that the change in kinetic energy is equal to minus the change in potential energy. It becomes a little easier if we put everything on one side. Where we're saying that when some sort of process happens, the total change in kinetic energy and potential energy add up to be zero. Now, let's just sort of flesh this out a little bit so it's a little bit more obvious that we're saying that energy is conserved. So the change in kinetic energy is final minus initial. Likewise, change in potential energy is final minus initial. Now we could put initial things together and final things together. If we put the final terms together and set them equal to the initial terms, which seems to make sense because these are both negative up here, we end up saying that there's this sum that we're looking at, the sum of kinetic energy and potential energy. And what we have as a sum in the final case is equal to what we have in the initial case. You might be wondering, what do I mean by initial and final? It could be any sort of scenario where things change, like a ball rolling down a hill or being thrown up in the air. We choose one point to be the initial point and another point to be the final point. And that's simply, what we mean by initial and final. We're just choosing 2 points in a process or in motion. But what we then say here is, you can see that we're adding kinetic and potential energy in both cases and seeing that those sums are equal. It might make more sense to just think about that the sum of the kinetic and potential energy is just representative of the total energy. And you can see then that what we're saying is the final energy is equal to the initial energy. This is conservation of energy. In physics, we are going to come across a couple conservation laws, and so we're going to start seeing them in this chapter and in upcoming chapters. Anytime we conserve something, we say that whatever that something is, we have a certain amount of that when we start, and we have the same amount when we finish. So for conservation of energy, we have a certain amount of energy when we start, and at another point, which we call the final point, we have the same amount of energy. Energy is conserved. Now, it's not true that anywhere, in any situation, energy will be conserved. There are some restrictions or some qualifications that allow us to say that this is true. In order for energy to be conserved, we don't want any energy to be lost to the environment, and that might happen by something like friction, or we don't want some external force to come and do work on the system, like I'm pushing with my hand, because that will change the amount of energy that the system has. And so both of those forces, friction and that external push, would actually be classified as what we would call a non-conservative force. So we cannot say that energy is conserved when we have non-conservative forces acting, but if the only forces that we have acting in a system are conservative, then energy will be conserved. Kind of seems like a circular argument, but I actually will explain in more detail in a later video what we mean by or how we define a conservative force. But in any case, what we want to remember right now is energy can be conserved if the only forces that are acting on the system are what we would call conservative forces. Let's look at an example. We have a 1 kilogram ball, and it's at the end of a 2-meter string, and it's swinging in the vertical plane. Just means it's going in a circle, in a vertical circle. And we're actually told that the speed at the bottom is 10 meters per second. And we want to know what is the speed at the top of its path. So that would be when it's upside down. Yeah, I know my circle isn't very good. It's a little not circular, but let's pretend it is. And we're going to call, when the ball is at the bottom, we're going to call that our initial point. And when the ball is upside down, or the whole thing is upside down and the ball's at the top, we're going to call that our final point. And so we want to figure out what is the, what's the speed when it's up there. We're going to use conservation of energy, because the only force that is acting or doing work in this scenario is the work of gravity, and that is a conservative force, because we have the potential energy due to gravity, and so that's how we factor it into this situation. So we're going to start with the conservation of energy. I already told you that at the bottom, we're going to say that's our initial point, and at the top, it's going to be our final point. We also need to designate where we're going to say y equals 0, because of the fact that gravity, the potential energy of gravity is given by mgy. So we need to be able to say where is y 0. So based on that, when we are looking at the initial time, we have the initial kinetic energy is given by 1/2 mv initial squared. But our potential energy initially is 0 because of the fact that we let that be our y equals 0 point. Kinetic energy when it's at its top is 1/2 mv final squared, and then the height when it's at its top, so the way we're going to write its final gravitational potential energy is mg times 2r, because the radius is 2 meters and it's going to be 2 of those above the initial point of y equals 0. And so this allows us to be able to calculate the final velocity, because all these other terms we actually know what they are. So we have 1/2 mv initial squared minus 2 mgr is equal to 1/2 mv final squared. And we can start rearranging things. First of all, I can get rid of the mass. It turns out the mass doesn't matter because it's in every term, so I can divide through by the mass. I'm also going to multiply by 2, so I get vi squared minus 4gr is equal to v final squared. And so v final is the square root of v initial squared minus 4gr. And the initial velocity was 10, and then minus 4 times 9.8 times 2, and take the square root of that, and we find the velocity is 4.65 meters per second. Okay? So that's going to allow us, you can see how the conservation of energy allowed us to be able to find that velocity. There's a second part to this question where we're actually going to be using some of our force knowledge. So we're going to keep that in mind, that V final was this, and let's make some room to be able to do the work for the next part of the problem. So this is just a reminder that this is the velocity of the ball when it's at the very top. We also see that at the beginning it was 10 meters per second. The next part is we're asking what is the tension in the string when the ball is at the bottom and the top of its path. So let's look here. This is where we're going to draw forces, and we're also going to be thinking about centripetal acceleration. So here's the ball at the bottom. There's the force of gravity acting on it. There's the tension in the string. And I'm just drawing the acceleration to remind us that as it goes in a vertical circle, the centripetal acceleration is going to be upward when it's at the bottom of its swing. So for forces, my acceleration I'm going to express as my centripetal acceleration. So we're using Newton's second law, but we're looking at the sum of the forces, but they're going to be along the radial direction because I'm looking at the centripetal acceleration. So this is where my components, I'm not talking about x and y, but in this case I'm talking about radial being the direction. Radial is along the line that goes from the object to the center of the circle. The two forces that I have are tension and the weight. And that's equal to mass times acceleration. Now, I do want to make note that I am thinking about what should be the sign on the acceleration. You can see here that tension I made positive, and that was pointing up. Gravity was negative, it was pointing down. The acceleration, as I noted here, would be pointing up as well, and that's why it has the same sign as the tension here. So I'm going to solve for tension because that's what they want me to find. I factored out the mass because it was in both terms. This is v squared over r. At the bottom, the speed was 10 meters per second. The radius is r. And here I would have gravity, which is 9.8. If I solve for that, I get a tension of 59.8 newtons. And so that's at the bottom. Let's look at the top. Nope, use a different color. When the ball's at the top of its flight, the bob is at the top and the string is hanging down from it. Well, it's not hanging, it's pulling. And so the direction of some of my forces is changing when I draw them on my free body diagram. I moved over the weight just so I could separate the two and both see them at the same time. Of course, they would act at the same location. But I can see that the tension in the string pulls down, gravity's pulling down, and actually the acceleration, because it's at the top and the centripetal acceleration is towards the center of the circle, it is also pointing down. So here, when I look at forces equals mv squared over r, things are going to look a little different. So using all these negative signs just to emphasize the fact that I'm paying attention to what direction forces and acceleration are in. And so I'm also using a more traditional sign or convention where down is negative and up is positive. So both my tension and my gravity are forces that act downward, and so I'm making them negative. My acceleration is also negative, and so, is also downward, so I make that negative as well. You can see I got a lot of negative signs. I'm not a big fan of a situation like that. I can just multiply the whole thing through by a -1 and just make everything positive. And then if I solve for t, you can see the tension's going to be different this time, because now instead of adding the gravity to the centripetal expression, I actually subtract it. So I get m times v squared over r minus g. Now for the velocity, I have to remember what the velocity was. That's why I left it here. It was the 4.65 squared over the radius, which is 2, minus 9.8. And so I see that the tension is actually very small. It's only like 1 Newton. And if you think about this, this might make sense in your experience. If you have an object, if you're swinging it around in a vertical circle, you know that you actually have to have it going fast at a certain speed so that it continues and it doesn't like go slack. If it went slack, the tension, of course, would be going to 0. So it does make sense that when the ball is upside down or at the top of its path, our tension is going to be smaller than it was at the bottom. And here it all works out with the math. Peekaboo. So the question is, though, what happens if we have a non-conservative force? If we have a non-conservative force acting on the system, it turns out that our energy isn't constant. And so instead of having the total change in energy being 0, it's not 0, but it's equal to the work done by the non-conservative force. And so if that work is negative, then it means actually that the final energy is smaller than the initial energy, and the energy is going to be decreasing. And that would be the case for something like friction. If the energy is increasing, it's because we did work through an outside force that wasn't a conservative force, which would add energy to the system. And so our change in energy would be positive. So you can see the top of my head, and to move on so you can see the top of my head, that's the purpose. Let's look at an example of how we would deal with this. So in this case, we're told a boy throws a ball up in the air. It has an initial speed of 20 meters per second, but when the ball returns, it's only going 17 meters per second. And so we want to know how much work air resistance did on the ball during its flight. Well, because we're talking about air resistance is just a type of friction, if you will. And so we know that there's a non-conservative force acting on the system. So we can say that the work for the non-conservative force is equal to the change in the energy. And so this change in energy is the change in kinetic plus the change in potential. So in a sense, if we throw the ball up in the air, it's going to go up, it's going to come back down, but this becomes our initial point and this becomes our final point, because we just talked about it returning to where it was originally. Now, initially, so we're going to just let this here because this is what we're trying to find. The change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. And the change in potential energy is mgy final minus mgy initial. Now this is actually equal to 0 because y final is equal to y initial. So it doesn't matter what I let this be. I'm just going to call it 0. That could be another thing. But even if I called y initial 10, I would still get no change in potential energy. All the change in energy in this scenario, we're going to see through the change in kinetic energy. And if we do the calculation, we find that this is minus 13.9 joules is the work done by the air resistance. The air resistance was the non-conservative force. The work done, C, is negative, but if you think about it, it makes sense because the whole nature of air resistance is that it's going to be a force acting against the motion. So anytime the object is moving, like say to the right, the air resistance is exerting a force to the left. So it's always going to be doing a negative amount of work. The other thing to think about is that this represents the total change in the energy that the ball has. And the ball actually lost energy because of the air resistance. And that's why this value is negative. So this is how we approach a problem when there's air resistance or friction or any other non-conservative force. In the next video, well, actually I don't know if it's the next video, but in another video, we see what conservative forces, how do we define them.